Hello again. Another application to systems is network flow. What is network flow? Well, a network, it says here in the first paragraph, consists of a set of points called junction or nodes, with lines or arcs called branches connecting with some or all of the junctions. There's a little example here on the right. So this point right here is called a junction or a node. And then the branches are here. The branches are the lines or the arcs. And network flow has a direction. The direction of the flow in each branch is indicated, and the flow amount or rate is either shown or denoted by a variable. So here the flow looks like it's, in this example, the flow looks like it's left to right, and the flow is in each branch. So this branch, the flow coming into this junction is 30, or this node, and then coming out of it, it's each one that has 2, and they're denoted by variables x1 and x2. So the second paragraph says that the basic assumption of network flow is that the total flow into the network equals the total flow out of the network, and that the total flow into a junction or a node is equal to the total flow out of the junction. Which means the total flow in is always the total flow out. Back to our figure 1, we can see here that the total flow into this node is 30. Doesn't give us any units, so I'm just going to put 30. And that is going to equal to the total flow out of this node. So by our branches, that would be x1 plus x2. Has to be the total. And you can see this if you continue reading the second paragraph. I'm just going to read the very last sentence of the second paragraph. It says here that the problem of network analysis is determine the flow in each branch when partial information, such as the flow into and out of the network, is known. And there's many examples of network flow. That is what the last paragraph here talks about. So let's go ahead and read that. It says a system of linear equations arises naturally when scientists, engineers, and economists study the flow of some quantity through a network. For instance, urban planners and traffic engineers monitor the pattern of traffic flow in a grid of city streets. That's going to be our first example. In example 2 down here, we're going to see traffic flow. Electrical engineers calculate current flow through electrical circuits. An economist analyzes the distribution of products from manufacturers to consumers through a network of wholesalers and retailers. For many networks, the system of linear equations involves hundreds or even thousands of variables and equations. So putting things in matrices is going to be valuable. So let's check out that traffic flow example. So it gives here a figure. The network in figure 2 shows the traffic flow in vehicles per hour over several one-way streets in downtown Baltimore during a typical early afternoon. So we're going to determine the general pattern, the flow pattern for the network. So what we would like to do is everything to flow nice and easily. So again, we want our total flow in to equal our total flow out for each node or junction. So I'm going to start with A here. And remember, the total flow in equals the total flow out. So for junction A, 300, what that means, if you remember up here, it says in vehicles per hour. So there's 300 vehicles per hour coming in Pratt Street, 500 coming in this way, which is Calvert Street. So the two flow ins are going to be 300 vehicles per hour plus 500. So 800 vehicles per hour is coming into node A. The flow going out looks like it's x1 plus x2. What is x1? x1 again is the flow, the traffic flow in vehicles per hour coming out of Pratt Street. So we have here x1 plus the x2, which is the flow out from junction A on Calvert Street. That was just A. Now let's look at B. What is the flow in from B? The flow in from B looks like it's x2, that same x2, but now we have coming in from Lombard Street, x4. x2 plus x4. What's the flow out? The flow out is x3 here plus that 300. The 300 coming out of Lombard Street. So let's do the same thing with node C. So the flow-ins are going to be 100 and 400. The flow-outs are x4 plus x5. Node D is only a three-way traffic since there's a harbor there. So the flow-ins are going to be x1 plus x5, and then the only flow out is that 600. Now we also want the total flow into the whole network to be the total flow out of the network. So the total flow into the network should equal the total flow out. And this is to keep things running smoothly. So what is the total flow into the network? Well, 300 from Platt Street, 500 from Calvert, 400 from Lombard, 100 from South. That should equal the total flow out, which is what's remaining. That looks like the 300 from Lombard, 600 from Pratt, and then this x3 here, this unknown from Calvert. So now we have a system of 5 equations. The last one actually is known. If we just solve for x3, we know it's 400. You could put in a 400 here, and that's how you would make it 4 equations instead of 5. So let's go ahead and simplify this to make it look a little better. So we're just going to x1 plus x2 is equal to 800 from junction A. Junction B, we saw that x2 minus x3 plus x4 better equal to 300. Oh, and I have an x5, so I better move that to the right. x4 plus x5 better equal 500. Let's see. D looks good. x1, I'll just line these up here, plus x5 is 600. And I did forget E. X3 is 400. I'll keep the x3 there, so that way we won't confuse what our variables are. Let's put this in matrix form. So here's the system as an augmented matrix. We could go ahead and solve this by hand since there's only ones and negative ones and zeros on the left-hand side, so it wouldn't be too hard to solve by hand. But I'm going to go ahead and use a calculator because it's going to be a lot of steps since this is a 5x6 matrix, and we want to get this in reduced echelon form just in case there's a general solution and not a specific solution. So here's my calculator. The first thing we want to do is type in the matrix. So we're going to go to second matrix, and I'm going to go to edit. It's a 5x6 matrix. I already typed it in here, but you can just type in a 5 here and press enter, and then a 6 and enter. And then you could just start typing in left, right. 1, enter, 1, enter, 0. And don't worry, 0, 0, 800 there. Don't worry that you can't see the whole thing. I'll just bring you back to that next line, and then you're going to type in the next line and so forth. If we go to the right here, you can see that the next line is correct. So once you've done typing in your matrix, then you're going to go to second quit to get out of here. Otherwise, it will do something inside this matrix. So you have to get out of this matrix. That's important. And then you're going to go to second matrix again. And this time we're going to go to math. We want to do some math with it. And this is, I'm going to go up. If I press up, it's a little bit shorter. I'm looking for RREF, Reduce Row Echelon Form. So I just hit enter once I have that highlighted. And reduce echelon form of what? We need to go back to our matrix. So we go to second matrix a third time. And this time we just go to names. We just go to 1. That puts it there. You can do the right parentheses if you want, but you don't need to. I'm just going to press enter. And there is the solution, or there is the reduced row echelon form. So let's copy that to our screen. So that is the solution. So I just copied that matrix over, and now rewriting this to solve our system, we can see that X5 is the only one free. Here's a pivot in each of these columns. X5 is free. So X1 is 600. I bring that over, minus X5. X2 is 200 plus X5. X3 we knew was 400. And finally, X4 is 500 minus X5. There is the general solution. And you can leave it like this, or you can write it in parametric form. So X would be X1, which is 600 minus X5. X2 would be 200 plus X5, all in terms of that one free variable, except for this one, that one's just 400. And X4 is 500 minus X5, and X5 will just leave as X5. So we can see that the constants would be 600, 200, 400, 500, and then there's no constant here, so that would be 0, plus X5, some variable, some t, times negative 1, 1, 0, negative 1, 1. So you can see there's an infinite number of solutions. X5 is free, so it could be anything. So let's choose X5 as 100, for instance. If X5 had 100 vehicles per hour flowing through it, X1 would be 500, X2 would be 300, X3 is 400, X4 would be 400, and X5 would be 100. So here would be the X when X5 is 100 vehicles per hour. This is just a specific example. There's many different solutions. So let's look at the constraints a little bit more generally by considering this practice problem. It says, consider the network flow studied in this example, example 2, determine the possible range of values for X1 and X2. So I just rewrote the solution here. So the hint here says that the example showed that X5 is less or equal to 500. So let's go ahead and do that first. By the way, a negative flow is not good. None of these can be negative because the negative flow would correspond to a direction opposite that is shown in the model. So we don't want a negative flow. So we're going to assume all of these are positive. So what I'm going to do is let X4 be positive. I'm going to use this last one here to get 500 minus X5 is bigger or equal to 0, which means X5 is smaller or equal to 500. The reason I didn't use the first equation, because that would mean that X5 would be smaller or equal to 600, and this is a stronger argument. So the hint continues to say, what does this imply about X1 and X2? So now we're going to use this fact, looking at X1. And what I'm going to do is I'm going to solve for X5 here. Since X5 is less than 500, and we know X5 has to be positive, all of them has to be positive, I'm going to say that X5 is between 500 and 0. And then that's the same thing as 600 minus X1 between 0 and 500. And I'm going to solve that. So solving for X1, I'm going to subtract 600 from all three expressions to get this line, and multiplying everything by -1, I get X1 is between 100 and 600. Since my time is up, here's the solution to X2. You can try it on your own. You can use the second equation here, and this is the answer.